Okay, we're going to try to finish up 16 today. We're going to do some more of those case of A's. And again, there's a chart with them, you guys. I will completely put that in there for you so you can look them up, okay? But if you're going to do, to find the pH, if you know the case of A, what you do is you have to write a chemical equation for the ionization equilibrium. And the one practice problem, I had you do this before, I did that for you, okay? Then we have the constant expression, and then you're going to set up a rice table, okay? They have ice table, they just do initial change in equilibrium and then equilibrium. I still like to put the R in there because then you can put in whatever your reactant is and whatever your products are, okay? So concentration is determined from equilibrium, just like we did before. Then you substitute in, and again, I know it's weird with the X, because like when you get your change in concentration for your reactant, it's going to be, whatever the concentration minus X. But X is a really small number. It's going to be like 0.000004, whatever. So you make the assumption that you're just going to use whatever the concentration is. And again, it's easier to solve. Otherwise, you have to set up quite equations and do all this other stuff. And it's such a tiny number that it doesn't really affect it that much. So that's the way we'll do it. And that's the way I had to do the problem before. Okay, I hope that the example that I set made it easier for you to understand. Okay, here's another example. Calculate the pH. We got a 0.3 molar solution of acetic acid. Okay, and I'll give you the chart. Do I have the case of A? The case of A for acetic acid, you can look up on this chart. Most of the time it gives it to you a problem, but again, I'll show you it. I'll show you where to find it. So again, 0.3, and now we're going to take this solution, and you guys, you can either write H plus or H3O, either or. Just take this one and take off an H. Okay, break it down into its ions. So if you want to do H3O, that's fine. If you want to do H plus, that's fine. Either way, they mean the same thing. But their concentration are 0 and 0. So I took this equation, okay, and I broke it down. You don't have to worry about the water. These solutions are aqueous solutions, so those you have to worry about, but because this is, a liquid, remember when we did equilibrium, we didn't worry about solids or liquids. So it tells us our molarity. These guys are 0. So these are their change is going to be minus X plus plus. So the products are always plus and the reactants always minus, same thing. So again, this is going to be this minus, and since these started at 0, they're X. And again, this is just like the problem you already did, practice problem, okay? The case of A is in a chart, 1.8 times 10 to the 5th. And I will put this, after this lecture, I'll have that chart for you so you can have it. But again, it's going to be my two products over my acid that I started with, okay? Then when we go here, okay, we set that up, plug in the answers. So these are both X, and this is, so it's basically going to be X squared over 0.3, because again, remember this is an approximate, is going to equal whatever our case of A is. And again, I wrote all that in. We don't want to have to use a quadratic formula to solve it. So we're just going to say this is 0.3, because X is a pretty small number. Okay, so again, our case of A is in a chart. We look it up, 1.8 equals X squared over 0.3. So then we take this number times 0.3 equals X squared. Then take the square root of that, and you get 2.3 times 10 to the 3rd. Okay, so again, what I did here is I moved this over, so I took 1.8 times 10 to the negative 5th times 0.3 equals X squared. And then I took the square root of that number. That gives me 2.3 times 10 to the negative 3rd. And again, look back at the problem that you just did. I had an example for you. That's how you do it. Then what you do is you just take the log of 2.3 times 10 to the negative 3rd. And again, you're going to get negative 2.64. Remember, we dropped that negative, okay? Because it's negative the log of. And that's how you do it, okay? So again, and look at that example that I gave you, and I'll give you some more, I promise. Sometimes, though, we just did acids where they just have one hydrogen. They move that one hydrogen. What if you have polypropic where they have more than one? Like, if you look here, here's carbonic acid. It's H2CO3. So you have a case of A for the first hydrogen, and you have a case of B for the second one. And here, here's phosphoric, H3PO4. You actually are going to have 3 listed because there's going to be, for taking away the first hydrogen, there's going to be one for taking away the second hydrogen, and there's going to be one for taking away the third hydrogen. And the numbers are up here, and you can see A sub 1, A sub 2, A sub 3. I'm just going to work with the first one because, it gets more and more complicated. But I just wanted to make you aware of that if you have an acid with more than one hydrogen, you can end up doing, 3 different steps to it. So if the factor in case of A, first, second, those are the dissociation factors. And again, there's 3. Third is the most you'll see. Okay. So the pH is going to depend on which one. We're just going to do the first association. We're going to just do this first column. Okay. But there are more. Again, I'm just making you aware of them. Okay. If you have a weak base like ammonia, remember, is the only one that doesn't have OH listed second. Okay. Kind of works the same way. We have here, we take and we add a hydrogen to make it an acid, and then because we took away a hydrogen, we have our base. You're going to set it up the same way. You're going to put this guy, its association, its concentration on the bottom, and these guys on top. And again, it works out just like we did the acids. The equilibrium calculation work is the same for acids as you did for base. You use the base association constant for NH3, and again, I'll have a chart with those. Okay, this is a different one because it has nitrogen. It doesn't have the OH in it. Okay, and the reason for that, it's an organic derivative of ammonia. They're called amines. We're not doing organic, but the reason why it gets to be a base is it disassociates and it actually causes these. It causes water to produce the OH, so it's still considered a base. Okay, it's a weak base. Okay, there are 2 main categories of weak bases. Okay, there's ammonia, and here's these are some organic ones, and then there's our OH. Okay, neutral substances with an atom non-bonding pair that can take in hydrogen. Okay, so because remember we said we have proton donors or hydrogen donors, those are acids, and then we have bases, which are hydrogen acceptors. Okay, so that's one example. And then our anions of weak acids, again, where we get the OH, but they don't disassociate. So bases are the same like an acid. If they break down into their ions really well, if they disassociate, then they're strong. If they don't, they kind of hang together, don't really break down into their ions, they're a weak base. So it works the same as an acid, same thing. And here's your associations again. This is right from your book. See, ammonia becomes NH4. Here's its case of B. Here's some other ones. Okay, they're constant. And again, I don't expect you to memorize these or know that you'll have a chart with them in it. So you just have to look up the case of B. And honestly, if you want to find the case of B and you know the case of A, they equal 1.4 times 10. I mean 1.0 times 10 to the negative 14th, just like they did before. So if you know one, you can find the other. Take that 1 times 10 to the negative 14th and divide them, and you'll get your case of A. So it works the same. Okay, so again, we're going to do a pH. Now we got a base instead of an acid. What is the pH of 0.15? We're going to set up our table. 0.15, these guys are zeros. Negative x, plus x, plus x. And again, remember when we do this, when we set this up, we're just going to use this. We're not going to use the minus x because it's a really, 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 really tiny number. And it just doesn't affect it that much. So we got to take and write it out. So we know that NH3, that's what we started with, plus water. That's not in our equation because it's a liquid. We end up with these two. These are 2 products. Basically, this is ammonia plus a hydrogen. And then because it gave one of its hydrogens there, what are we going to have left over? Hydroxide. So those are our 2 products. And then we have to find our case of B. Look that up. That's in a chart. You don't have to know those. You just look them up. Okay, so then we're going to solve it on the next page. Okay, we got this formula. And again, we're going to lose this guy. Okay, so 1.8 times 10 to the negative 5th equals x squared over this. So we're going to multiply these 2 numbers. They're going to equal x squared, and then we're going to take the square root of it, and that's going to give us our answer. Okay, so again, when you're solving this point, move this over and multiply 1.8 times 10 to the negative 5th times 0.15, and then take the square root of that. You can leave it all on your calculator and just, plug it in. Okay, and again, for calculators, guys, you don't need graphing calculators. You can just use a simple one like I have. I can do everything on here. I hope you can see that. They work just fine. Okay, if you have a graphing calculator, great. They work too, but you don't have to have one. That's what I'm trying to say. Okay, so we have this number, 1.6 times 10 to the negative 3rd. That's what x equals. So, okay, this was a base. All right, so if I take the log of this, I'm going to get the POH, which is 2.8. Remember, the question asks, what is the pH? So I can just take 14 minus 2.8, and then I'll get my pH as 11.2. All right? Or the other thing is, you know, I took the log of this. You can take 1 times 10 to the negative 14, you know, figure out that answer, and then take the log of that number. Either or works, but honestly, it's easier just to take the log of this number, and you get 2.8. That's the POH. So if you want the pH, take 14 minus 2.8, and you'll get 11.2. That's the easiest way to do it. Okay? I'm always about easy. Okay? The relationship between A and B, when you got a conjugate acid and a conjugate base pair, case of A and case of B, if you multiply the two of them together, you're going to get case of W. Case of W is 1 times 10 to the negative 14. So here you have HF. If you take this number times this number, you're going to get 1 times 10 to the negative 14. If you take this number times this number, you're going to get 1 times 10 to the negative 14. They always equal that. Okay? So if you know one, you can always calculate the other. The thing to remember, and it's just like when we did the pH and the H3O and the concentrations, case of W, the constant for water is 1 times 10 to the negative 14th. Always. It never changes. Okay? So, when you have an acid and a base and you put them together, okay, if you can react them, you can neutralize them. And one of the things they always make is a salt. They make salt and water when you react them together. And we'll talk more about that next chapter because we're going to do titrations. You can actually calculate what concentration you need to add to neutralize stuff. But the reaction with water, because you get hydrogen and hydroxide, is called hydrolysis. Okay? To determine whether salt is an acid or a base, you need to look at the cation, the positive metal, and the anion separately. All right? So the cation, the metal, can either be acid or neutral. It can't be a base. Okay? So the cation can be acidic or neutral. The anion, they are, because there's nonmetals have so many more electrons to deal with, you can either make them acidic, basic, or neutral. So they're more flexible. But the cation, the metal, can either be acidic or neutral. The anion can be all three. Okay, so you can determine that. Here's a chart, and again, I got this right out of your book. If you take a group 1 or 2, so the alkali metals or the alkali earth metals, okay, they're very strong. Okay, so if you put one of them with a base, or with water, excuse me, when you dissolve in water, they'll be neutral. This is the salt that they're making. Okay, so like if you take HCl, hydrochloric acid, plus a base, sodium hydroxide, you're going to end up with NaCl, salt, and water. Okay, and salt would be neutral. Okay, because you've got that sodium is a group 1 metal. And again, the group 2 ones too, barium, magnesium, those guys, same thing. Okay, if you take them and you put them with a weak acid, okay, then they're going to act like the anion, they'll be basic. Okay, group 1 and metal cation with an anion of a weak acid. Okay, so then they're going to end up being basic. And then if you have the transition metals would be like copper and iron, the ones in the middle. Okay, if you put them with a strong acid, you're going to end up with a very acidic. And again, these are in your book. You don't have to memorize them. You can just look them up, you guys. Okay, but the thing to remember about these most often is the case of A and the case of B. Okay, the case of the equilibrium constant for the acid, if you take its conjugate base, when you put these two together, when you multiply them together, you're going to get 1 times 10 to the negative 4. So you can always figure out one if you know the other. Okay, and again, an oxyl acid, like HCl, is not, because that's just hydrogen and chlorine. Okay, or HBr or whatever. But a lot of the acids you'll see, like sulfuric acid, is H2SO4. It has oxygen. So there's hydrogen, oxygen, and one other element. Okay, we have hypochlorous, hypobromous, hypoiodic. Okay, another sulfuric, phosphoric. All those guys, they have hydrogen, oxygen, and another element. And they have their dissociation constant. And again, you can just look at them on the chart. You don't have to know them. Generally, as their electronegativity of the nonmetal increases, and again, that's on a chart, the acidity for the acids the acidity increases. Okay, so here you have hypochlorite.